So I'm trying to work backwards to find an integral of the motion. I'll come back to it. So this job is done. You have all the thetas as functions of t. You have all the i's, they're constants of the motion. And now the job is to go back to the original q's and p's, and you have an explicit formula if you can invert this. So you really have a problem where you have, by the way, I could call theta it minus omega it equal to constant of the motion determined by this initial value here. Therefore, I have n time independent constants of the motion, n time dependent constants of the motion, and therefore that's enough for me to integrate the whole thing. And the problem is solved. In principle, you're not told how to find these f's, nor are you told what's the significance of these f's or anything like that. But at the moment, this is what it is. You need to find this many constants of motion, and then you're guaranteed by this theorem that the system is integrated. There are lots of problems which you can check out in general. But given an arbitrary Hamiltonian, there's really no simple way of checking out if it's integrable or not. Right? Let's look at an example. Let's look at the two-dimensional oscillator or something like that and see how this fellow works. So there are, in standard textbooks, there are ways of finding the action variable and then the corresponding angle variable, etc. I'll just write it down for the harmonic oscillator since all of you are familiar with it. And let's make matters a little interesting by not looking at a 1 degree of freedom system, which is always integrable. There's a Hamiltonian immediately. But a 2 degree of freedom system where this is not guaranteed. You have a 4-dimensional phase space. So let's look at the 2D oscillator. You can regard it in two ways. Either you have two independent oscillators with different masses, different frequencies, or you have one oscillator on a plane connected by a spring to this, connected by an anisotropic spring or two anisotropic springs, so that the spring constants in the x and y directions are different. And then you have all these Lissajous figures and so on. So what does a Hamiltonian look like? H looks like P1 squared over 2m1 plus 1/2 m1 omega 1 squared q1 squared plus P2 squared over 2 plus 1/2 2 That's your Hamiltonian. Now what do action angle variables do? Well, it's easy to check that the following are in fact the action angle variables. So, yeah. Whichever way you like. It's a two oscillators. That's a special case. I'm just taking the most general case possible. Two different masses. The mass is not very relevant here. Later I'm going to go to a very special case of this where the masses are equal, frequencies are equal and so on. Because that problem has some very special symmetries. What are the action variables here? Well, you know that if you choose I equal to 1 over omega I times pi squared over 2m plus 1/2 mi omega I squared qi squared, I equal to 1 and 2, and theta I equal to tan inverse of mi omega I qi, so that the dimension is right over qi. If you choose these, yeah. Pardon me? There's no coupling. They're two independent degrees of freedom. So the matter is integrable, very trivially. It's very trivially integrable because I look at this and I have qi pj equal to delta ij, etc. Then it's immediately clear that I have two constants of the motion. Here's f1 and here's f2. And you're guaranteed that f1, f2 is 0. Because 1 and 2 variables have nothing to do with each other. Therefore, it's integrable by the Liouville-Arnold criterion immediately. That will always be the case if I write an n-body Hamiltonian, n degree of freedom Hamiltonian as a sum of one-body Hamiltonians decoupled. It will always be true. I have n of them in involution. So, the theorem is applicable, and now I ask what does it look like in the action angle variables. I leave you to verify this, of course, a standard exercise that theta I ij equal to delta ij. and the thetas Poisson commute among themselves, so do the i's. So it's clear that these are action angle variables. Canonical transformation, Poisson bracket is preserved. I urge you to check that the Jacobian of the transformation is +1.
Sir, how did you got these expressions at the first place?
How did I get this? Okay. There's a prescription for writing down the action variable, the p dx and so on. And then you have to find the generating function of this transformation. And in this case, this particular Hamiltonian is completely trivial. It's just quadratic. So you get you know the motion, essentially. More complicated cases, there's no simple way of finding out these i's and b's. In principle, you can write down formulas, but no way of finding out whether it will integrate or not. Okay. But in this case, it does. I urge you to pay attention to the fact that this is not the same as going to polar coordinates in each QP plane. It's not going to, that's not a canonical transformation. Going to polar coordinates from xy to r theta in plane polar is not a canonical transformation, doesn't preserve measure. So canonical transformation, by our definition, must have the Poisson bracket structure preserved and volume elements preserved, or area elements, whatever. Both are necessary. We will see a simple case where one will be satisfied but not the other a little later. So once you verify that this is a canonical transformation, the question is, what does a Hamiltonian do? So it's clear that since it's all time dependent, the Hamiltonian, the new Hamiltonian K, is the old Hamiltonian in which the variables in it, little q's and p's, are expressed in terms of the i's and p's. So there's nothing else to it. Therefore, K of I1, I2 is equal to I1 omega 1 plus I2. Well, that's easy to verify. It's trivial. From here, it's immediately obvious. So what are the omegas? Omega 1 and omega 2 themselves, I differentiate, and they're constants. They're constants, two different constants. So you know theta I of t, you can integrate the matters over. The important thing is to check that these are indeed, this in fact forms a canonical transformation. And it's a trivially solvable problem in this case. However, the question is the motion periodic or not? Now you see, I can represent this motion because the i's are constant. In the I1, I2, theta 1, theta 2 space, I can represent this motion in terms of just the motion of whatever is moving, namely the thetas are changing. So two angles, theta 1 and theta 2, each of them running 0 to 2 pi. Therefore, the space is a torus. Because a torus, one angle would be of points on a circle. The second one, if you like, is orthogonal to it, and therefore the motion is on a torus. And this is how a torus emerges naturally for periodic motion. So let's say angle in this direction with respect to some reference point is theta 1, and angle in this cross-sectional direction is theta. So the motion has got reduced to T2, the two torus. For each given I1 and I2, there's such a torus. For each given I1 and I2, the only thing that changes is theta 1, theta 2. So if in the original QP space, Q1, P1, Q2, P2 space, this was your first phase trajectory, this is the other phase trajectory. Then the size of this ellipse is fixed by the value of the Hamiltonian, which is in the words I1, and similarly for I2. And the position of the phase space point on this is fixed by one angle, which is essentially related to theta 1. And the other one is theta 2 here. And motion proceeds by theta 1 and theta 2 changing. Pardon me? No, I'm not looking at the extended phase space. But they're time dependent. So what? So what? I project it onto the original phase space. It doesn't matter. In the original phase space, motion is still happening, right? I do not have 2n time independent constants of the motion. Then it would stop. Some of them are time dependent, I don't care. And it has restricted the motion in this action angle variable space, it's restricted it to two angles. So I could take the diameter of this torus to be I1 or radius to be square root I1, whatever, and the other fellow to be square root I2. So this, whatever it is, those are fixed, and you have motion, which just tells you where is theta 1, where is theta 2. Motion occurs on this torus. Every time oscillator 1 completes a full revolution, the representative point does a full circle of this. Every time it oscillates once fully, 2 oscillator oscillates, it does a full circle of this. Now it's clear that the motion will wander around on top of this torus, and it will come back to the original point if and only if omega 1 over omega 2 is a rational number. Then the time period is related to the greatest common denominator, whatever, GCD of the two. But otherwise, the motion is not periodic. As you see when you project this phase space onto the Q1, Q2, P1, P2 thing, very popular presentation is when you put Q1 and Q2, you project this 4-dimensional phase trajectory onto Q1 and Q2. And what do you see? Well, each of them is a harmonic oscillator with some amplitude. So if the two frequencies are equal to each other, then the general projection here is some kind of ellipse. If the frequencies are in some rational ratio to each other, like 2:1 or something like that, then you start seeing figure of 8 curves, do things like this. But if the frequencies are irrational, then you see something which is filling up in this crazy fashion. Of course, it seems to intersect itself, but remember there is a 2-dimensional projection of a 4-dimensional trajectory, which does not intersect itself. What are these figures called? Lissajous figures. I thought they were all eliminated from the syllabus, but it's there. So you see these pictures with 2 pendulums with sand going around, etc. And you have these beautiful patterns. But what you do know is that if the frequencies are not commensurate with each other, the motion is not periodic. However, it comprises 2 different periodic motions with frequency omega 1 and omega 2, and that's called quasi-periodic motion. On the torus. Now you generalize this to the n-dimensional case and you say, if the system is integrable, then there are n angle variables, and these n angle variables will move on the surface of an n-dimensional torus, which is the direct product of S1, S1, S1 n times. And the motion is periodic if and only if all ratios of frequencies are commensurate. If even one of them is not commensurate, you are in trouble. This motion will then start filling, space filling part of this n torus. In the case of 2 frequencies, you can look at it in the following way. You can ask, let me take a cross section of this torus and ask what that looks like. The cross section, let's assume the time period here is 1. And then every time at the end of 1 second it comes back to itself, I ask where it is on the cross section circle. Then on that circle, this is the initial point. After 1 time unit, this thing orbits and comes back and intersects the circle somewhere else. And after 1 more time unit, it comes and intersects it somewhere else. And so on. And you wait long enough, it will intersect it over and over again at various places. And then the question asked is the following. Given that after n such revolutions, let's call it theta. I shouldn't use the word symbol n. Let's call it k. At time unit k, after k seconds, this is equal to theta k minus 1 plus some constant number. It's increasing each time by a certain constant number. So some irrational number alpha modulo 1, modulo 2 pi. Because angles are defined up to modulus 2 pi. Let's in fact divide this by 2 pi and call this xk equal to xk minus 1 plus some beta modulo 1. So I make the circumference of the circle unity. And then I say, okay, I take a number between 0 and 1. It's somewhere on that circle in the x space. And each time, after each time unit, you're adding an irrational number alpha, or beta. And the question is, what happens to this thing? This problem was solved long ago by mathematicians. Weierstrass or somebody solved this long ago. And the answer is very interesting. It says, if this number beta is rational, then every point, no matter where you start, comes back to itself sooner or later. So every point on this unit interval, closed such that it's become a circle, comes back to itself after a finite amount of time. Every point, guaranteed to come back. Every initial condition is part of a periodic orbit. On the other hand, if this beta is irrational, then you're guaranteed that no point comes back to itself. No point will come back to itself. That means the motion for all initial conditions is quasi-periodic. Moreover, you have another theorem that says, and this is rigorously provable, the iterates of any initial condition, you start here x0 and then x1, x2, it keeps going, it never comes back to itself. After some time it comes here and then it comes here, etc. The iterates of any initial condition will uniformly and densely fill the entire torus. And uniform. That means the population density, right? The density of such points, of these iterates on this torus is uniform. Uniform probability density. Every little patch of equal area is like to be equally frequently visited as time goes on. Yeah, this is ergodic. And moreover, the iterates of any initial x0 come arbitrarily close to all points on this, which is ergodic. So if you started with a set of initial points in this small interval, points of this interval are going to visit arbitrarily close to all points in this phase space, given enough time, and fill this whole thing uniform. No single point will ever come back to any point it's visited earlier. So you're beginning to see, yeah.
So if this project is high on the if the omega 1 and omega 2 are rational,
Yeah.
you are saying they won't be phase-splitting.
Right.
Now, if you sit on a phase-splitting matrix,
Yeah.
and you are likely to have an intersecting magic which is not phase-splitting.
No, they will not intersect. I'll show you the magic by which it happens. That's a good point. Let's look at the trajectories on this torus and see what happens. How did I get to this torus at all? I said, look, I had four-dimensional phase space, and then the motion got reduced in some change variables to a two-dimensional surface. And the motion is happening on this two-dimensional surface. Okay. So two of the integrals of the motion, the constants of the motion, are precisely I1 and I2. Now you agree that I1 and I2 are nice analytic functions of the Q's and P's. They're algebraic functions. P squared plus Q squared, P1 squared plus Q1 squared, P2 squared plus Q2 squared. The third one cannot be an isolating integral. It must be something which is not a smooth curve, because if the motion was periodic, then it would perhaps do this a few times and then come back and join, etc. And it's not filling the torus. It's not ergodic on the torus. Points are not going and filling up the whole torus, right? There's only a very small portion of the torus, infinitesimal area on the torus, zero area on the torus is being filled up by a periodic orbit here. So this means that the third integral of the motion is also a nice smooth analytic function. But in the case when they're incommensurate, suddenly, magically, this must become a very complicated space-filling curve. But you can see how that's going to happen, because I pointed out that theta 1 of t was equal to omega 1t plus theta 1 of 0, and theta 2 of t equal to omega 2t plus theta 2 of 0 in this manner. And therefore, it follows that this, of course, implies that t equal to well, let's compute theta 1 of t over omega 1 minus theta 2 of t over omega 2. This is equal to theta 1 of 0 over omega 1 minus theta 1, sorry. Yes, theta 2 of 0 over 1. Each of them is t. Which implies that this quantity is a constant of the motion. So the third isolating integral of the motion is f3. f1 was this, I1, f2 was I2, and the third fellow, f3, is equal to 1 over omega 1 tan inverse of m1 omega 1 q1 over p1 minus 1 over omega 2 tan inverse m2 omega 2 q2 over p2. That's your constant of the motion. It's a horrible non-algebraic function, multiple value. It's not an isolating integral at all. So that's how this magic occurs. Now, I urge you to find out what happens if omega 1 is equal to omega 2. Then this, you use the formula for tan inverse, put the masses equal, etc., and you'll end up with a simple algebraic function. It is reduced to tan inverse of a simple algebraic function, and if that function is constant, so is the tan inverse. So this will suddenly become an algebraic function and an isolating integral. Otherwise, it's in general a non-isolating integral. Very complicated. Yeah? No, I can have many constants of the motion. Why should it be, for integrability, I need to find n constants of the motion, which are actually isolating integrals, which will be in involution with each other. That's important. And that I found in this problem. I found f1 and f2. But there are more constants of the motion, because the motion, as you pointed out, is happening in 2n dimensional phase space, or 2n plus 1 dimensional extended phase space, and you need that many constants of the motion. You need 2n of them. Some of which, at least one of which, has to be time dependent. So we found n of them which are time dependent. There may be lots of combinations of them, but two things. They must be in involution with each other in the original case. And then they must have nice analytic properties. They must be isolating integrals. This motion has is a 4-dimensional phase space. Therefore, there are 3 constants of the motion. And this third constant of the motion, which is time independent here, is in fact not an isolating integral. And this follows not in involution with the other 2. So I shouldn't use the word F3. I use constant of the motion. Let's say C3. I should call it F3 because I use F for things which are in involution with each other. In an integrable n degree of freedom Hamiltonian, you can only have n constants of the motion in involution with each other. Less than n is not integrable. More than n, it's overdetermined. You can't find it. It's not consistent. How do I check an irrational number? I can't, right? It's finite, it's truncated. So I try to find, I'll come to this when I talk about maps. Because on a computer, I mean, much of the models of chaos we're going to talk about are all to do with being able to generate irrational numbers. But of course, on a computer, everything got finite truncation and then it's gone. So what one does is to check, make a number as irrational as possible. There are degrees of irrationality. You choose a number to which any rational approximation is very bad. You try and choose a number like that. Since we raised the point, let's settle it right away. Let's look at numbers between 0 and 1 because that's all the numbers there are. Then, several ways of writing this, but let me choose a favorite way of doing it, an easy to see way of doing it. So let's start with the number x between 0 and 1. And I can always write this x in standard continued fraction form. So I can always write this as 1 over some a0 plus 1 over a1 plus 1 over a2 plus 1 over a3. If this finishes at some point, then it's a rational number. If it goes on forever, it's an irrational. It may go on forever, but recurring. I don't care. It's like a recurring decimal which could be made. rational number if you put it in decimal form. But in the case of continued fractions, if it goes on forever, it's an irrational number. If it terminates, it's of course a fraction and a rational number. Now it's clear that if you choose a number such that one of these a's is much larger than 1, then it's a very good approximation. That rational number is a very good rational approximation, because suppose this is 6, that is 8, and that is 6022 or some 6084 or 87. Then I can truncate it there, and that particular fraction is a very good rational approximation to this number. It would be very bad news if all the numbers were of equal magnitude. Then you don't know where to stop. And what's the worst case scenario? What's the absolutely worst case where rational approximation is really bad? Everything is 1. If everything is 1, then that's the smallest integer, non-zero integer. So you have this guy. In a sense, that's the most irrational number of all. This is the most irrational.
So the first appearance of the large number.
Pardon me?
One will consider first appearance of the large number.
Yeah, so I'm saying that if one of these denominators, one of the AIs is a large integer, large positive integer, then you can truncate it at that point and say whatever rational number results is a very good rational approximation to your irrational number. That means that irrational number is very close to this rational number. But this irrational number doesn't have such a good rational approximation. Wherever you stop, after a certain state, your error is quite significant. It's quite large, because all these fellows are 1s. And you're leaving out a fraction compared to 1. What's this number equal to? So this number satisfies x equal to 1 over 1 plus x, which will imply the positive root at least, x equal to root 5 minus 1, which is equal to a number between 0 and 1. Yeah, 0.618. Yeah, it's the golden ratio. Root 5 plus 1 over 2 is the reciprocal of this number. 1 point something or the other. So, it's immediately clear that this irrational number is very bad to approximate by a rational number. Therefore, if I want to choose a number on a computer that's close to an irrational number, I'll take this to 25 or 99 decimal places in between. You would still say, it will still be rational, therefore our broader iterations will come back. Then something called a shadowing lemma comes to my help, which says that in a truly chaotic system, for a truly chaotic orbit, they're guaranteed to exist periodic orbits of arbitrarily large period, which will shadow the true chaotic orbit. So in a sense, if this is your true chaotic orbit, there exist very close rational numbers which will sort of shadow this and then maybe turn back and come around. Then there's another fellow which will shadow this for a much longer time and then turn back and come around, etc. So there exist such orbits. And on the computer, you're really following one of those guys. So that's it helps to know that there is such a lemma and it works. Otherwise, you'd never be able to discover true chaos. Right? So I'll come back to this map. This is a map, right? So it says, take each x and take its reciprocal and subtract the 1 over the integer. Subtract this. And the fixed point of this map will give you this number, golden. What happens if you did this 1 over 1 plus 1 over 2 plus 1 over... That's also a pretty good number. 2 is here. It's also an irrational number. It's square root of 2 minus 1. That's the next best. That's the silver mean. Then you can do root 3, 3, 3, 3, 3, etc. And that's the proper mean or something like that. And if you do 1, 2, 1, 2, 1, 2, you get something in between. And that's a fixed point of the once iterated continued fraction map. That's also a nice irrational. And so on. So there are a lot of algorithms for generating these fellows. So this fact that the third integral of the motion is non-isolating Tells you how these functions, innocuous looking as they are, it's an integrable system, still leads to quasi-periodicity, which is the next in complexity after periodicity, and some torus is getting densely filled up. Now, of course, in general, these tori don't need to get densely filled up at all, and moreover, the size of this tori will depend on the energy in some sense. Now, lots of properties in n-dimensional phase space depend on the number of degrees of freedom, because if you have n equal to 2, you have 4-dimensional phase space